Module 24, Lecture A, PCA SVD. By the end of this lecture, you will be able to apply PCA and interpret explained variants and components, use incremental, sparse, kernel, and MiniBatchPCA variants appropriately, and apply truncated SVD for sparse high-dimensional data, such as text features. PCA Basics. Principal Components. Principal component analysis finds new data-driven directions that capture the main patterns of variation in a dataset. It rotates the original features, so the first direction explains the most variation, with later directions explaining less. This can combine correlated measurements, such as floor area and sale price and housing data, into fewer uncorrelated dimensions, making analysis and visualization simpler. Principal components combine the original variables using weights called loadings, which show how much each variable contributes. These loadings help explain what a component represents, such as a shared pattern or a contrast between groups of variables. The relative signs of the weights matter, but flipping all signs does not change the component's direction. Overall, a principal component reorganizes the data to make its strongest patterns easier to see. Principal components help simplify datasets with many related variables, such as images, finance data, or customer behavior. They capture major patterns, like overall brightness in an image or broad preference trends in analytics, before smaller details. However, they are mathematical summaries that maximize variance, not automatic explanations of real-world causes or importance. To interpret them well, you must examine their weights, the original variables, and the data context. Python code, principal components. This example illustrates how principal component analysis finds new directions for correlated features. It rotates the data onto new axes, showing how much variance each component captures. We import key Python libraries for data analysis and visualization. NumPy supports numerical work with arrays, while Matplotlib creates visualizations. From Scikit-Learn, we use principal component analysis to reduce data dimensions while preserving variance, and a StandardScaler to put features on a comparable scale before analysis. We create a small, reproducible dataset with controlled randomness. A random number generator is initialized with a fixed seed, then used to generate 80 values from a normal distribution with mean 0 and standard deviation 1. These values form the initial size feature, which will be used to build correlated features later. Random noise is added to the size values to create an area score that varies slightly while staying generally related to size. A price score is then created by scaling size and adding a separate amount of noise. Together, these steps simulate two real-world features that are correlated with the same underlying variable, but differ in scale and variability. The area score and price score are combined into one two-column matrix using NumPy's column stacking function. This creates a dataset with 80 rows and two correlated features. The matrix shape is then checked to confirm the data was prepared correctly, and an error is raised if the expected dimensions do not match. Before applying principal component analysis, we standardize the features using Scikit-Learn's StandardScaler. This makes each feature have a mean of 0 and a standard deviation of 1, so features with larger scales do not dominate the analysis. After fitting the scaler and transforming the data, the scaled features can be compared more fairly based on their variation. We create a principal component analysis model with two components, so it finds two new axes that capture the most variation in the standardized data. Transforming the features projects them onto these axes, producing principal component scores. These scores represent the data using new, uncorrelated features that emphasize the main directions of variance. The code reports the Scikit-Learn version to support compatibility and reproducibility, then summarizes the PCA results. It shows how much variance each principal component explains, rounded for readability, and displays the area and price weights for the first and second components. These values help explain how PCA transforms the original features into new directions in the feature space. Create a Matplotlib figure and axis. Then make a scatter plot of the principal component scores, with the first component on the horizontal axis and the second on the vertical axis. Use slight transparency so overlapping points are easier to see, and add gray reference lines at 0 to mark the origin. Finally, title the plot, label both principal component axes, and display it. This script shows how principal component analysis works on a small dataset with two strongly related features, like area and price scores. After standardizing the features, it transforms the data into two principal components and reports how much variance each component explains, along with the feature weights. The resulting scatterplot shows the data in the new component space, making it easier to see the main directions of variation. Centered SVD. Principal component analysis begins by centering the data, which means subtracting each feature's mean, so values are measured as deviations from the average. This shifts attention from raw values to patterns of variation. Singular value decomposition is then applied to the centered data to find the main directions where those deviations vary the most. Centered singular value decomposition, or SVD, is closely related to principal component analysis. It finds the main directions of variation in centered data, measures how much variation each direction explains, and gives each observation coordinates along those directions. This helps summarize correlated features, such as student scores across subjects, by revealing overall patterns and contrasts without manually choosing variable combinations. In principal component analysis using centered singular value decomposition, preprocessing strongly affects the result. Centering makes components describe variation around the mean, rather than being driven by large feature averages. If features have very different scales, they should be standardized so large range variables, such as income, do not dominate smaller scale ones like blood pressure. With proper preprocessing, the components provide a lower dimensional view that preserves the main structure of the data. Explained variance. Explained variance shows how much of the original data each principal component captures in PCA. The components are ordered from the most variation to the least, so the first component represents the strongest pattern in the data. For example, in housing data, a main component might combine floor area and lot size to summarize property size. If it explains a large share of the variance, the data can often be reduced to fewer dimensions, while keeping its main structure. The explained variance ratio shows how much of the data's total variation is captured by each principal component. It helps you decide which components are important enough to keep when reducing dimensions. If a few components capture most of the variation, as can happen with image patterns like brightness or edges, compression can work well. But when variation is spread across many components, reducing dimensions may remove important information, especially in complex datasets. Explained variance in PCA should be interpreted in context, not just by size. A component with high explained variance may reflect broad patterns like age or market trends, while smaller components can still reveal important signals, such as disease indicators or sector behavior. Because PCA is sensitive to variable scales, standardization is important, and explained variance should be considered alongside component loadings and the goals of the analysis. Python code, explained variance. This example explains how PCA uses components to summarize standardized wine measurements. The explained variance shows how much information those components retain. We import the main tools needed to analyze the wine dataset with principal component analysis. NumPy supports numerical work, Matplotlib handles plotting, and Scikit-Learn provides the dataset, preprocessing, and modeling tools. The wine data is loaded, standardized with StandardScaler, so features are on the same scale, and then prepared for dimensionality reduction using PCA. We load the built-in wine dataset from Scikit-Learn and use its feature data for analysis. These features are numerical measurements for each wine sample, organized as a matrix that can be used in later processing. Before using principal component analysis, confirm that the feature data is valid. It must be a two-dimensional matrix with at least 2 columns, since PCA needs multiple features to analyze variance. If the data does not meet these requirements, the process should stop with an error. Standardizing features prevents variables with larger units from dominating the model. A StandardScaler is used to transform the data, so each feature has a mean of 0 and a standard deviation of 1, making the features easier to compare. Create a PCA model with a fixed random state so results can be reproduced. Then fit it to the standardized features to find the principal components, which capture the main directions of variation in the data. This prepares the model to transform the data into a new coordinate system based on those components. Convert the PCA explained variance ratios into percentages to make them easier to interpret. Then, compute their cumulative total to see how much overall variance is captured as more principal components are included. The code reports the Scikit-Learn version for reproducibility, then summarizes key PCA results. It prints how much variance the first principal component explains, the cumulative variance explained by the first 2 components, and the number of components needed to capture at least 90% of the total variance. This helps show how effectively PCA reduces the data's dimensionality. This plot shows how cumulative explained variance increases as more principal components are included in the PCA of the wine data. The component numbers are plotted against the cumulative variance, with markers showing each point. A dashed horizontal line marks the 90% variance target, making it easy to see how many components are needed to reach that threshold. The chart includes clear axis labels, a title, a legend, and a y-axis range that keeps all values visible. This script uses principal component analysis to measure how much variation in the wine dataset is captured by each component. After standardizing the features, it reports the variance explained by the first component, the cumulative variance from the first 2 components, and the number of components needed to retain at least 90% of the dataset's information. It also creates a cumulative variance plot with a 90% reference line to help show how many components are sufficient. PCA variance. Whitening features. Whitening is applied after principal component analysis to make transformed features uncorrelated and scaled to the same variance. This helps algorithms that are sensitive to feature scale, such as distance-based classifiers and neural networks. By preventing high-variance components from dominating, whitening can make later processing focus more evenly on important patterns, such as finer details in facial recognition. Whitening makes PCA transformed data more balanced by giving each component equal variance. This prevents distance-based or dot product-based models from focusing too much on high-variance directions while missing smaller but useful patterns. It is especially helpful in tasks such as image preprocessing, anomaly detection, and sensor analysis, where subtle signals may still be important. Whitening changes the PCA representation by making components equally scaled, which can also make low-variance noise more noticeable. Because of this, it is important to keep only useful components and avoid emphasizing weak, unstable patterns. Use whitening when another algorithm needs decorrelated, standardized features, but use standard PCA when you want to interpret which directions contain the most variation. Python code. Whitening features. This example contrasts standard PCA with PCA using whitening. Whitening rescales the retained components so their variances are equal, and the printed values highlight this change in scale. We import NumPy for numerical work and Scikit-Learn for machine learning tools. From Scikit-Learn, we use principal component analysis to reduce dimensionality while preserving variance, a classification data generator to create synthetic test data, and a StandardScaler to normalize features. Standardizing the data helps principal component analysis focus on relationships between features rather than differences in scale. We create a synthetic classification dataset using Scikit-Learn's make classification function. It contains 300 samples with 5 numeric features, including 3 informative features and 2 redundant ones. A fixed random state makes the results reproducible, giving a controlled dataset for exploring transformations such as PCA. We standardize the features using Scikit-Learn's StandardScaler, so each feature is centered around its mean and scaled to unit variance. This helps PCA focus on the data's correlation structure, rather than differences in feature scale. The scaler's fit and transform step learns the scaling from the data and applies it in one operation. The code validates that the input is a 2-dimensional table with exactly 5 numeric features. If the data does not match this expected shape, it raises an error explaining the required format. This early check helps prevent problems in later analysis by ensuring the input is structured correctly. 2 PCA models are set up to reduce the data to 3 components. The plain version keeps the original variance structure, while the whitened version also rescales the components so they have equal variance. Both use a fixed random state, so the results are reproducible. We first apply standard principal component analysis to standardized features, reducing the data to 3 components while keeping as much variance as possible. We then repeat the process with whitening, which also scales the components to unit variance, so they are uncorrelated and equally scaled. We compare ordinary PCA with whitened PCA by measuring the variance of their transformed components. For ordinary PCA, the variance shows how much each principal component contributes to the total variation in the data. For whitened PCA, the same check confirms that the components are uncorrelated and scaled to have equal variance. The output first shows the Scikit-Learn version to support compatibility and reproducibility. It then compares ordinary PCA and whitened PCA by reporting how much variance each component explains and how the transform scores vary. The key point is that whitening keeps the PCA components uncorrelated while rescaling them to have equal variance. This script compares ordinary PCA with whitening PCA on standardized synthetic data. Both methods reduce 5 features to 3 components, but ordinary PCA keeps the original variance pattern, while whitening makes the component variances equal. The printed results show the explained variance for ordinary PCA and the transformed variances for both methods, illustrating that whitening produces uncorrelated components with equal variance when that scaling is useful. Incremental PCA. Incremental PCA is a form of principal component analysis designed for large or streaming datasets. Instead of loading all data at once, it processes smaller batches and updates the principal components over time. This makes it useful when memory is limited, while still preserving the main structure of the data in a compact form. In incremental PCA, batch size affects both efficiency and result stability. Smaller batches save memory but can produce noisier updates, while larger batches give steadier estimates but require more memory. The goal is to choose a batch size that preserves the scalability of incremental processing while keeping results consistent with standard PCA. Incremental PCA is useful when standard PCA is limited by memory, very large data, streaming input, or the need for repeated updates. It is not automatically better than standard PCA, which can be simpler and slightly more accurate when the full dataset fits in memory. To use it well, prepare the data consistently, especially with centering and scaling when features use different units. Overall, it keeps the main benefits of PCA while making it practical for large-scale workflows. Python code, Incremental PCA. This section demonstrates incremental PCA using manageable batches of data. It compares the batch-based approach with ordinary PCA, then reviews the explained variance and the resulting two-dimensional projections. We import the main tools needed for this machine learning workflow: NumPy for numerical arrays, Matplotlib for plotting, and Scikit-Learn for modeling utilities. From Scikit-Learn, we use a synthetic classification data generator, standard and incremental principal component analysis for dimensionality reduction, and a StandardScaler to normalize features so PCA is not affected by different feature scales. We create a reproducible synthetic classification dataset with 1,200 samples and 12 numeric features using Scikit-Learn's make classification function. 6 features directly inform the target, while 4 are redundant combinations of those informative features. This produces correlated data that is well suited for demonstrating dimensionality reduction methods such as PCA. Before fitting the decomposition models, the code verifies that the dataset has 1,200 rows and 12 features. If the dimensions are different, it raises an error instead of continuing. This check helps ensure the input data is correctly structured and prevents problems during model fitting. Before applying principal component analysis, the features are standardized so differences in scale do not distort the results. A StandardScaler adjusts each feature to have a mean of 0 and a standard deviation of 1, and the fit transform method both learns these scaling values and applies them to create the scaled dataset. Incremental PCA reduces the data to 2 dimensions by processing scaled features in batches of 150 samples. For each batch, the model is updated using a partial fitting method, so it learns progressively instead of loading the full dataset at once. This makes PCA practical for large datasets that may not fit into memory. After the incremental updates, the scaled data is transformed with the learned incremental PCA model. This projects the full dataset onto the principal components, producing a 2-dimensional view that preserves the most important variance found during training. We first build a standard PCA model as a baseline, reducing the scaled data to 2 principal components with a fixed random state for consistency. The model is then fit to the data and used to create a 2-dimensional projection. This result provides a reference for comparing ordinary PCA with incremental PCA. The output reports key details for comparing incremental PCA with ordinary PCA. It shows the Scikit-Learn version for reproducibility, the batch sizes used during incremental processing, and the explained variance ratios for both methods, rounded to 3 decimals. These values indicate how much information each principal component captures, and help assess how closely the incremental approach matches standard PCA. A Matplotlib figure and axis are created to set up the plotting area. A scatter plot then shows the first projection component on the x-axis and the second on the y-axis. Points are colored by class label with a variance gradient, using small, partly transparent markers to make overlapping points easier to read. The plot is finalized by adding a clear title that identifies it as an incremental PCA projection from batch updates. The axes are labeled as the first and second incremental principal components, and a legend distinguishes the data classes. The visualization is then displayed for viewing. This script shows how incremental principal component analysis reduces a standardized dataset to 2 dimensions by processing it in smaller batches, making it suitable for data that may not fit in memory. It compares the result with ordinary PCA, which processes the full dataset at once and reports the explained variance for both methods. The final visualization colors the reduced data by class to show how well the 2-dimensional projection separates the samples. Sparse PCA. Sparse PCA is a form of principal component analysis that makes results easier to interpret by using only a small number of original features in each component. Instead of giving weight to every variable, it sets many weights to 0, so each component is tied to a clearer set of meaningful variables. This helps identify which features most influence the data structure, such as important product categories or genes, while reducing the complexity of standard PCA. Sparse PCA is a version of PCA that favors simpler, easier to interpret components, even if they capture slightly less variance than standard PCA. This makes it useful when explanation or feature selection matters, such as identifying key economic indicators in finance or specific patterns in images. Choose Sparse PCA when clear structure is more important than maximizing variance alone. Sparse PCA works best when features are centered and scaled, especially if they use different units, because the method is sensitive to scale. The key choice is the sparsity level. Too little can make components hard to interpret, while too much can hide important relationships. Testing several levels helps find stable, meaningful components. Overall, Sparse PCA creates compact, interpretable representations, such as small groups of related terms in text analysis, that are easier to explain to stakeholders. Python code Sparse PCA. Sparse principal component analysis makes components easier to interpret by focusing on a smaller set of original features. This comparison shows how sparse loadings differ from dense loadings and highlights which features are selected. We import NumPy for numerical work and random number generation, then use Scikit-Learn for machine learning tools. From Scikit-Learn, we bring in principal component analysis and sparse principal component analysis, where the sparse version can make components easier to interpret. We also use a standard scaling tool to center features and scale them to unit variance before applying principal component analysis. We create a small, reproducible dataset by using a fixed random seed and generating 180 samples. Each sample has 3 normally distributed hidden features, which represent the underlying structure that will be used to simulate the observed data. A weight matrix links hidden features to observed features, with each observed feature mainly tied to one hidden group. Small random noise is added to mimic real-world variation. The observed data is then created by combining the hidden features through the weight matrix and adding this noise, producing noisy measurements that still reflect the underlying hidden structure. We first define the feature names to identify the survey and spending categories in the data. Then we standardize the features with Scikit-Learn's StandardScaler, which centers the data and gives each feature unit variance. This ensures all features contribute fairly during decomposition. First, we confirm that the scaled dataset has the expected shape, 180 samples and 6 features. If the dimensions do not match, an error is raised to stop the process. This check helps prevent later analysis from running on data with the wrong structure. We compare standard principal component analysis with sparse principal component analysis using 2 components on scaled data. Standard PCA reduces dimensionality while preserving as much variance as possible, while Sparse PCA adds a sparsity control so the components rely on fewer features and are easier to interpret. Both models are fitted to the data so we can compare how they capture the dataset's underlying structure. A threshold of 0.2 is used to identify significant feature weights. For both ordinary PCA and Sparse PCA, we count how many component loadings exceed this threshold in absolute value. Comparing these counts shows how sparsity changes the number of important features in each component, helping assess interpretability. The code first reports the Scikit-Learn version to support compatibility and reproducibility. It then compares ordinary PCA and Sparse PCA by counting how many feature loadings are large enough to be considered significant for each component. Sparse PCA usually has fewer significant loadings, which can make its components easier to interpret by focusing on the most important features. For each of the two Sparse PCA components, we examine the feature loadings to see which features contribute most. Features with loadings above a chosen threshold are treated as significant and saved for further analysis. Their loadings are rounded for readability, and a short summary is printed for each component. This makes it easier to interpret Sparse PCA by highlighting the most influential features. This script compares standard principal component analysis with sparse principal component analysis on synthetic data with hidden feature groups and added noise. After scaling the data, both methods extract two components, and the script counts how many features have meaningful loadings using a threshold of 0.2. Sparse principal component analysis usually produces fewer important loadings, making the components easier to interpret. The output reports the Scikit-Learn version, compares the loading counts, and identifies the features that most influence the sparse components. TruncatedSVD, MiniBatchSparsePCA. MiniBatchSparsePCA helps analyze large, high-dimensional datasets efficiently by learning from small chunks of data at a time. Unlike regular PCA, it sets many feature weights to 0, making the results easier to interpret. This makes it useful for tasks like finding key patterns in student messages, such as financial aid questions, without processing every word in detail. MiniBatchSparsePCA reduces high-dimensional sparse data efficiently by processing it in small chunks, which helps when the full dataset is too large for memory. It keeps results interpretable by emphasizing the most important features instead of many small, less useful ones. This creates a clearer, more compact representation for analysis and decision-making. TruncatedSVD and MiniBatchSparsePCA serve different goals in high-dimensional data reduction. TruncatedSVD is best for efficiently reducing sparse, uncentered text data into dense, lower-dimensional representations. MiniBatchSparsePCA is better when the goal is to learn sparse, interpretable components and update them incrementally. In short, choose TruncatedSVD for efficient matrix reduction and MiniBatchSparsePCA for finding meaningful feature patterns. Python code, MiniBatchSparsePCA. This example shows how MiniBatchSparsePCA finds compact transformed features by focusing on small groups of important features. It highlights how sparse components can make the reduced representation more concise and easier to compare. This setup imports key tools for numerical computing, machine learning, and text processing. NumPy supports efficient array operations, while Scikit-Learn provides machine learning utilities. The MiniBatchSparse principal component analysis tool helps process large datasets in smaller chunks. And the CountVectorizer converts text documents into token count matrices for machine learning. A small set of short text documents is created. with each document focused on one topic. Some documents discuss exams and grades, others cover tuition and financial aid, and the rest describe login or error issues. This dataset will be used to build a sparse matrix that records how often each word appears across the documents. CountVectorizer turns text documents into numerical data by counting how often each word appears. Applying its fit and transform process builds a sparse matrix of token counts, which is efficient for large text collections. The feature names are the unique words found by the vectorizer, and they show which words correspond to the columns of the matrix. Before using MiniBatchSparsePCA, the word count matrix is converted from sparse form to a dense array because the algorithm needs dense input. The process also checks that the array has one row for each document. If the row count is wrong, an error is raised to catch problems in data preparation early. We use a mini-batch sparse principal component analysis model to reduce the data to 3 sparse components. The sparsity setting encourages many component loadings to become 0, making the results easier to interpret. Training processes 3 samples at a time, and a fixed random seed ensures the results can be reproduced. The word count data is used to train a MiniBatchSparsePCA model, which converts the original dense features into a smaller set of coordinates. These transformed document scores capture the main patterns in a more compact form. The model also provides component weights, showing how much each original feature contributes to the new sparse components. The code reports the Scikit-Learn version to confirm the working environment, then shows the size of the original word count data. It also shows the size of the data after Sparse PCA, making it easy to compare the original and reduced forms. This demonstrates how the transformation lowers dimensionality and makes the data more compact. To measure how sparse the component weights are, we estimate the share of weights that are effectively 0. Each weight is treated as near 0 if its absolute value is below a very small threshold, 1 times 10 to the negative 9. The average of these checks gives the proportion of near 0 weights, which is then reported rounded to 2 decimal places. For each sparse component, we examine the feature weights to see which words matter most. By ranking the weights by their absolute size, we identify the 3 strongest features for that component and match them back to their original word names. Printing these top words helps interpret what each component represents in the text data. We round the first document's transform scores to 2 decimal places to make them easier to read. These rounded values show the document's compact feature representation after Sparse PCA, helping us interpret how it appears in the reduced feature space. This script shows how MiniBatchSparsePCA can compress text document features. It first turns short documents into a word count matrix, converts it to a dense format, and then reduces it to 3 sparse components. The output compares the original and reduced matrix sizes, reports how many component weights are 0, and lists the most important words for each component. It also shows the transformed features for the first document, illustrating how the text is represented in a smaller feature space. Kernel PCA. Kernel PCA extends regular PCA to data with nonlinear structure. Instead of relying only on linear combinations, it uses a kernel function to compare observations as if they were in a richer feature space. This helps reveal complex patterns, such as nonlinear relationships in customer behavior, that ordinary PCA may miss. For sparse, high-dimensional text data, TruncatedSVD is usually more practical than kernel PCA because it works efficiently with document term matrices that contain mostly zeros. Kernel PCA relies on pairwise similarity matrices, which can be costly in memory and computation for large document collections. It may help uncover nonlinear patterns in smaller text datasets, but for large-scale text tasks, truncated SVD is typically the better choice, unless nonlinear structure is especially important. Choose between Kernel PCA and truncated SVD based on the data, scale, and purpose of dimension reduction. Truncated SVD is usually better for large, sparse text data because it is efficient and fits latent semantic analysis. Kernel PCA is more useful for smaller datasets where nonlinear similarities matter, but its results are harder to connect back to original features. In practice, Kernel PCA is mainly exploratory, while truncated SVD is the common scalable choice for text feature reduction. Python code, Kernel PCA. Compare nonlinear kernel principal component analysis with truncated singular value decomposition using small, sparse, text-like document features. Truncated singular value decomposition provides a linear reduction of the sparse data, while kernel principal component analysis can reveal nonlinear structure when it is present. Visualizing the reduced features helps show whether nonlinear patterns appear and whether the nonlinear method adds useful insight. This setup imports the main tools needed for text analysis, dimensionality reduction, and visualization. NumPy supports numerical operations, while Matplotlib creates plots. Scikit-Learn provides kernel principal component analysis and truncated singular value decomposition for reducing data dimensions, along with a TF-IDF Vectorizer for turning text into numerical features. Together, these libraries prepare the workflow to process text data, simplify its representation, and visualize the results. This example creates a small set of short text documents grouped by topic. 3 documents use legal terms, 3 use medical terms, and 3 use technology terms. These clear topic groups provide a simple dataset for later analysis and visualization. A TF-IDF Vectorizer converts text documents into numerical features for analysis. It creates a sparse matrix where each row represents a document, each column represents a unique term, and each value shows how important that term is within the full document collection. This prepares the text data for later steps, such as dimensionality reduction. The code verifies that the sparse text matrix has 1 row for each document. If the counts do not match, it raises an error to show that the document-to-matrix transformation failed. This check helps ensure the data is correctly prepared before later processing, such as decomposition. Truncated singular value decomposition reduces a sparse text matrix to a smaller number of dimensions. Here, the data is compressed into 2 dimensions with a fixed random state to make the result reproducible. The transformed points represent the documents in a lower dimensional space, making patterns easier to visualize and analyze. Kernel PCA is used to reduce the sparse text data to 2 dimensions while capturing nonlinear patterns. It uses an RBF kernel with gamma set to 0.8, which controls how strongly individual data points influence the transformation. The result is a new 2-dimensional representation that makes the data's underlying structure easier to visualize. The code reports key checks for a dimensionality reduction workflow. It shows the Scikit-Learn version for reproducibility, confirms the size of the transformed sparse text data, reports how much variance truncated SVD captures, and verifies the final output size from Kernel PCA. We prepare the data for visualizing Kernel PCA by assigning each document to one of 3 topics: legal, medical, or technology. An index array maps documents to these topic groups, and a matching color array gives each group a distinct plotting color. Together, these labels and colors make it easier to interpret the visualization by topic. A plot is prepared with a figure and axis. Then each topic is drawn as a separate group of points. For each topic, the matching data points are selected from the Kernel PCA results, using the first two components as coordinates. Each group is shown with its topic label, assigned color, and a larger point size for visibility. The plot is labeled to show Kernel PCA results for a small sparse text example, with the two axes representing the first and second Kernel PCA components. A legend identifies the topic groups by color, and the plot is then displayed so the transformed data can be visually examined. This script compares kernel principal component analysis and truncated singular value decomposition on text documents from legal, medical, and technology topics. The documents are converted into a term frequency inverse document frequency matrix, then reduced to 2 dimensions by both methods. TruncatedSVD captures the main variance in the sparse text data, while Kernel PCA with a radial basis function kernel highlights nonlinear structure. The result is a 2-dimensional view where documents form topic-based clusters, showing how Kernel PCA can reveal nonlinear patterns in the data. Sparse text reduction. Sparse text reduction helps manage text data with huge vocabularies, where each document uses only a small fraction of possible terms. Methods like term frequency inverse document frequency create mostly empty matrices, which are efficient to store but harder to analyze. TruncatedSVD reduces these matrices into a smaller set of latent features that capture the main patterns in the documents, such as broad themes like finance or health. TruncatedSVD reveals hidden semantic patterns in text by reducing noisy word-level data into broader latent components. This helps identify documents or complaints that discuss similar topics, even when they use different wording. By compressing large vocabularies into a smaller, more useful representation, it supports tasks such as clustering, classification, and grouping related customer support issues. When applying TruncatedSVD to sparse text data, choose the number of components carefully. Too few can blur distinct topics, while too many may keep noise and slow processing. Explained variance can help guide the choice, but it should be tested against task results such as classification accuracy or clustering quality. Overall, TruncatedSVD helps turn raw text features into a more useful form for machine learning, while keeping processing efficient. Python code, sparse text reduction. TruncatedSVD reduces sparse text data into lower-dimensional latent semantic features without converting the text matrix into a dense form. The result highlights how the reduced representation compares with the original dimensions. We import NumPy for efficient numerical work with arrays and matrices, and use Scikit-Learn for machine learning tools. From Scikit-Learn, the term frequency inverse document frequency vectorizer converts text into numerical features that emphasize important words. We also use truncated singular value decomposition to reduce the size of those features, while keeping the most important information. We define a small set of short text documents grouped by topic. 2 documents use medical terms, 2 use sports terms, and 2 use technology terms. These 3 clear topic groups provide a simple dataset for later reducing the text into latent semantic features. A TF-IDF Vectorizer converts the documents into a sparse matrix that captures how important each term is in each document, while reducing the weight of terms that appear often across the whole collection. Using the default settings, the fit transform method learns the vocabulary and applies the transformation in one step. The sparse matrix is efficient for large text data because it stores only non-zero values, saving memory. The code verifies that the sparse text matrix has 1 row for each document. If the counts do not match, it raises an error to signal a problem in the transformation process. This check helps confirm that pre-processing was completed correctly before any further analysis. TruncatedSVD reduces the size of a sparse text matrix while keeping its most important structure. Using two components maps the data into a two-dimensional space, and setting a random state makes the result reproducible. Fitting and transforming the matrix applies this reduction, producing a simpler version of the data that still preserves key patterns. To understand the first component, convert the vectorizer's feature names into an array. Then, sort the component's term weights by their absolute size. The largest weights show which terms influence the component most strongly. Selecting the top 5 terms gives a quick view of the main words that define that component. The output summarizes a dimensionality reduction workflow for text data. It checks the Scikit-Learn version, compares the original sparse matrix shape with the smaller reduced dense matrix, and reports how much variance the reduced features capture. It also shows the most important terms in the first component, and the reduced representation of the first document. This script turns documents into a TF-IDF sparse matrix, then uses truncated singular value decomposition to reduce the text data to 2 latent semantic features. It compares the original and reduced dimensions, reports how much variance is retained, and highlights the top terms driving the first component. The result shows how sparse text can be transformed into compact, dense features that preserve the main themes. In this lecture, you learn to apply PCA and interpret explained variance and components, use incremental, sparse, kernel, and MiniBatchPCA variants appropriately, and apply TruncatedSVD for sparse high-dimensional data such as text features. In the next lecture, Lecture B, we will go over factor components.
Thank you for your attention. See you all in the next lecture.